Thank you. So I decided to talk about this because I have a lot of servers that are not happy with the current state of CPU side channel attacks. So I started as, I'm chief system architect of SiteGround, but I started as a system administrator, and I really hate losing resources. I also help organize OpenFest, which is Bulgaria's, actually on the Balkans, the biggest FOSS conference. And this is why the last year I couldn't come because your conference is on the same dates. So first, before we start, this is not for general purpose use. In our case, we don't have general purpose applications. We have only web applications that run on our servers. Since we are a hosting company, we consider all code as hostile, because even if you are a good user, at a certain point you get hacked and somebody injects bad code on your site. So this happens constantly on our infrastructure. This doesn't remove the KPTI, the need for KPTI, but you can use it instead of it. So how many of you know what Meltdown is? Okay, that would be fun. So I assume that you guys don't know what flush interrupt and flush are attacks. Nice. I will explain this. So in January, some people disclosed an attack on the CPU that allowed to read the whole memory of the machine from user space, which, as you have to assume, is bad. The fixes for this, as they were proposed or discussed at that point, were talking about 10 to 15% degradation of the performance, which for your laptop is not a big issue, but your laptop is not affected by this because you don't run potentially bad code on your laptop most of the time. JavaScript here. So having this, I wasn't a big fan of adding all of this overhead to all of our servers. And having one machine is not a problem, but having thousands of machines, this means that we couldn't buy these machines that could account for these 10–15%. This doesn't work. Okay. So we started working with my team how to fix this without the overhead that Intel was proposing. So first you have to understand how CPUs work, and here you have a simplified diagram of a CPU. You have 4 different caches, actually. The fourth is not shown here on this diagram. On a single core, you have the layer 1 instruction cache and layer 1 data cache. And then you have the layer 2 cache, which is also instructions and data. And then you have layer 3 cache. And these are shared. L1 and L2 are shared between the hyperthreads, which means in a single core you can have 2 threads that are using the same cache. So the same memory can be accessed by 2 different processes. L2 cache is actually shared between all the execution engines. One CPU has a floating point, IS, integer execution engines. So these are different parts of the CPU, but they share the same layer 2 caches. And layer 3 caches are shared between all cores, which means that if something gets there in the layer 3 cache, you can actually access it from other CPUs, even though this is unrelated to your first program. So the basic idea here is that you have this complex CPU with a lot of things inside of it, and here you have data flowing from the layer 3 cache to the layer 2 cache to the layer 1 cache inside different parts of the CPU. And this is AMD Bulldozer architecture, but Intel's is similar, just a little bit more things inside of it. So 2013, the first entry vault attack was found. This is a side channel attack. And then in 2016, it was enhanced with the push attack. And I'll explain those first. First entry vault, you get a shared library. And since shared libraries are shared between different processes, they're actually mapped in the same memory format. So if you have this as a shared memory, it's mapped like this in the physical memory. And even though you have virtual memory, which are different addresses, other spaces for each process, the physical memory for this library, the physical footprint of this library is the same. Actually, I'll show this first and then I'll explain first entry vault. So you have this physical memory and this shared library, the kernel has mapped it on the same physical memory. So if you have one shared library in one virtual, in one process, you have the virtual memory space of this process that shares the same actual physical memory with another process. And this is not directly visible from user space. This is very important to notice. So let's get back to first entry vault. First entry vault says you will be using a shared library. Then you would be cleaning the caches of the CPU. After you clean the caches, you will wait for the victim that is using the same shared library to actually load the shared library in memory. This will actually load it in the caches, and then you time this request. So this means that if the data is not in the cache, the timing would be slower. Like if the data is in the cache, it would be around 50 cycles for the CPU to get the data and compute it. While if it is not in the caches, it would be, for example, 250 cycles to get the same data. And you can time this pretty accurately with the discrete timers of the CPU. So you can be sure that this is your data that was loaded. So the idea here is that you would find a shared library that you share with another process, like OpenSSL or anything that is very common on your infrastructure, and use this shared library to attack the machine. Every time you get the data from the caches, you would actually increase a counter in the CPU, and I'll talk about these counters by the end of the presentation. Then push. With first entry vault, you had to actually read the data from the caches to know if there is data that is from the shared library. Push uses the same shared library approach, then pushes the cache, and then waits for the victim process to get the data again into the caches. Then your attacker process is pushing again the cache. The difference here is that the second push would take longer time if there were data in the caches, and it would take less time if there is no data in the caches. So you again use timing only to get data that other processes on the machine actually used that library. And these are side channel attacks. These are things that you don't have full control over because these are in the CPU itself. You don't have control of how it is caching this data or for how long it is caching this data. You can always use CLFlush to actually flush the cache lines from the CPU, but this is the control that you have. You don't know when this is happening, and this is the very good thing about this side channel attack, because it's not directly using your you're not directly referencing this memory. You are simply checking the timings of the cache. So this is a simplified diagram of how a thread is executed in your CPU. You have the instruction hook aside buffer, translation hook aside buffer, which is your mapping between virtual and physical memory. And this is a buffer, this is a cache, this is another cache that you have. You have a branch predictor buffer, B2B, and all the instructions from there go to the decoder, and these are your assembly instructions, your moves, your jumps, this sort of instructions. They go to this decoder, and then from there, they're checked for, they're decoded from assembly instructions to micro operations in the CPU. These are different type of operations, a little bit obviously smaller. Then they're reordered because at certain point the CPU can see that some of your instructions are actually they will not get their data from the memory as soon as they're scheduled for execution. This means that the CPU will wait for memory to be copied in the caches, layer 3, layer 2, layer 1 caches. In order to speed up this, it simply reorders this micro operation later until the data is actually in the caches. So it will out of order execute other instructions in your CPU just to make sure that it uses the full potential of your CPU. And now you see here we have integer engine and floating point engine, and they actually execute the instructions, and then we retire everything from the CPU. With hyperthreads, we essentially have the same CPU, but with different engines at the end executing the instructions. So this is how hyperthreading actually works. You use the available execution engines in your CPU, and most of the modern CPU have tens and more execution engines, which means that they can execute multiple instructions at the same time, but we have 2 or 4 threads per CPU core. This means that these threads are sharing the layer 1 and layer 2 caches and layer 3 last level cache. So Meltdown changed everything by simply saying, okay, this out of order is pretty nice, and let's assume this. The first 2 lines, add and sub, are simply the functions adding and subtracting from certain addresses, from certain registers in the CPU. These are pretty simple, but you have to see that these are different registers. For both instructions, we use different registers. Since they don't interact with each other, they don't use the same registers one after another, this means that we can execute those out of order. If we have the data for these registers, we can execute them out of order. While with the second assembly, we here see that we are using the same ESI register for 2 instructions. This means that we cannot execute those 2 instructions directly out of order. Here it would be better to replace the FF, which is assigning just FF to register ESI, with another register in your CPU, because this will guarantee that it couldn't be executed out of order. In this case, actually, we can speculate that it also can be, sorry, bad example here, can be executed out of order. If you can execute an instruction out of order, this means that, for example, we can get data from memory before the if that is checking if this data is actually needed after that. So if you have a very simple if statement that says if array some index I is greater than 5, for example, you would execute this code. Else you would execute the other code. With the speculative execution, you don't know if the else is actually executed before the if statement. So the instructions are executed out of order and you get the data in the caches. This is not a problem architecturally because at certain point after we retire the data, we will see that this is the mispredicted branch. We have the branch predictor here, B2B. It mispredicted the data, the instructions. It executed them out of order because of their naming and rearranging of the micro operations. And in that case, we have in the cache of the CPU our data, but since we know that it was wrong, we simply don't retire this data and continue with the correct path. But since we don't retire the data from the caches, it stays in the caches, which means that if we are using, for example, force interrupt or force, we would get the data from the caches. This is the way you can actually get the data for all the processes. Unfortunately, every time you try to access a memory address that is not within your memory space, you would get a segmentation fault, as you know, which is quite nice, but you can fork a process or a thread that will segfault, and you would simply know that you can get the timing off of this and get the actual data that it was trying to access. Because of out-of-order execution, it is already in the cache. It's segfaulted, but because of out-of-order execution, you have the data for that memory address, physical memory address, in the cache. So, other protections, first protection that is currently in the mainline kernel is the kPTI. Each process before, each kernel before the latest 4.19 had, was it 4.19? Okay, in January we got a kernel that has kPTI. The situation is very simple. You have, before kPTI, a single process has had the whole memory of the machine mapped inside the memory space of the virtual memory space of this process. The differences between kernel memory and user memory. The difference is only in single bit that is checked when you are accessing the memory. If this bit is set, this means that that you require a privileged mode in the CPU to read this data. If you are not in privileged mode, this means kernel space, you cannot read this data, which is nice. However, if you now can read any address and segfault and get with force interrupt or force attack, get the actual data from the caches, you don't need to read at all the data that is in the memory address. You can side channel this. So kPTI is a protection that separates the kernel memory, physical kernel memory, from the physical kernel memory of physical user space memory for each process. You now have in the user space process only a few pointers to the actual kernel memory, and every time when you need to do a syscall, you actually have to change priority security rings in the CPU, which means that it would take a little bit more time to get data from the kernel to the user space or from user space to kernel space. Think of it as fuse drivers and stuff like this. Every syscall that needs to be called now cannot access your memory. You have to copy this data. Capsule 8 on January 5th showed that you can use performance counters that are currently collected from the kernel to mitigate this, not to mitigate, to detect this attack, because every time you segfault, you can get this from the CPU. Endgame on January 8th showed their research on this, and they simply showed only research, no code. Capsule 8 showed a little bit of code. I was already working on our solution at that point, and when I noticed this, we already had something working for our situation. So let's see what Capsule did. They used the page fault counter of perf to detect that there is a problem with something on your machine. There's something fishy here. Someone is trying to to start processes that are constantly segfaulting, which is not the normal way programs work, right? Endgame expanded this with transactional instructions. Since I don't have enough time, I'll skip the transactional instructions. Both of these solutions, they are detection only. They don't prevent the attack, while KPTI prevents the attack, but it costs you for each syscall. So what we decided to do is fight the attack itself, the exploit itself. So the exploit, in order to be working better on multi-core machines with a lot of processes running, requires to be set on the same core where the attacker process has to be running on the same core where the victim process is running. This requires the shared set affinity syscall. And we simply patch that and why to the user process that is issuing set affinity. Yes, we did that, but we actually don't do it. So the process itself doesn't know that it's not scheduled on the same CPU. We save the CPU mask that should be the new CPU mask in the task struct of the CPU, and every time if it is requested, we give this CPU mask instead of the actual CPU mask. So the process doesn't know that it doesn't run on the same CPU. The other thing was we started to collect data for each process that is dying. Segmentation fault of children or grandchildren or threads are collected, and also we can do this collect this information with the transactional instructions. So when child or thread dies, it will be accounted +1, +1, +1. Since on our infrastructure we are shared hosting, we don't have processes that simply segfault. If it segfaults, it's either a bad software that shouldn't run at all, or a hardware issue. Both cases we need to know this. And we decided, okay, we will stop each process that is segmentation faulting. Every time we do this, we first detect that there is a dying segmentation fault, and then we stop it. We don't kill it, we stop it. This means pausing the process, which is quite nice because the attack cannot continue. However, the attacker may decide, okay, if my process is stopped, I'll continue it. It's pretty simple. No, you can't on our servers. All signals that are going to these processes that were stopped are now only available to be continued by the host root and nobody else. So in order to account the segmentation faults, we created a new array in the kernel, and it counts for each bit the segmentation faults. Then we use a single-threaded work queue, which is a little bit of problem, and we created a proc interface. Now you can see this. We have this proc segfaults file. We have a process with this bit 23930 that has this many segfaults. This is without the limit. You see the current limit is 0. If we set the current limit to 1 and start new processes that segfault, we see this situation where one process had 2 segfaults and was stopped. Another process had 655 segfaults and it was stopped at that point. We can allow this many segfaults simply because the work queue is on a single processor, single core, which means that it would be woken up once every few times. Since we have like machines with 20 and 40 cores, this every few times depends. So we will allow a few cycles of the program to run, but then we will stop it. And let's see what's happening. This is from the kernel message. We see that there is a process that was halted because it had so many seg faults. And here's the attack. This is the actual code from the Meltdown GitHub. You task set affinity to this secret that is on the root user, and on the Meltdown user, you do the physical read from the same address. And the moment you start this program, because I did su to the Meltdown user, both the physical reader task and the su task are stopped. And with this, we prevent the attack. I'll skip this simply because we don't have time, but COFUSH is the instruction that is used in the CPUs to flush the cache. And unfortunately, this is an instruction and its brother COFUSH opt, they're user space instructions. They don't require privilege to be run. This means that you cannot easily capture them. The only easy way is to create a virtual machine, and in that virtual machine, capture the COFUSH and COFUSH opt. Unfortunately, if you issue an invalid instruction, it will implicitly run a flush of the caches. So I have given a lot of links at the end of this presentation. If you have any questions, I would be happy to answer.
Questions?
Here.
Thanks a lot for your talk. Two questions. First, did your changes break any valid user space which relied on set affinity, or?
We don't have a use case for our users to set affinity.
Okay.
So we have use case for set affinity on the host, like setting affinity for file system processes, or these are root on the host. And you can still set affinity on the root on the host, but you cannot do it in a container inside of it.
Okay.
So we didn't break anything. We simply added a few megabytes of RAM usage for the actual for the increase of task set and our array for the processes.
Another question. I didn't get, how do you use this work queue in the kernel? What was the purpose of it?
The idea is that there should be a process in the kernel that actually does the checking. So since we are accounting this in the array, PID array that I showed you, you need somebody to actually check it regularly. And you don't want to do it on every schedule interval. You want to do it on a single CPU on one schedule interval on this CPU, because otherwise you have to issue it on each CPU. It will cost you more resources, and we didn't want this. Because of that, obviously, other CPUs can actually execute this program that is attacking you at the moment, and this is why we had the 655 seg faults of the program before it was stopped. Simply because on the other CPUs, you can still execute until the work queue is executed on the CPU that is scheduled. So this was a trade-off, but since this would leak only a few kilobytes of RAM and will notify us of the problem, we were okay with this risk.
And do you check the number of faults in this work queue? What do you do?
No, we don't need to check this. So we check only the numbers in the PID array. You have a PID array that has a number for each process ID, and if there is more than 0, we have to stop this process. This is what it does.
And can you do it asynchronously during the page fault, during the fault handling? When the process dies, when the process is sent the signal, the seg fault, you can
We could either synchronously at the moment that it gets the signal check if this bit has had more. Unfortunately, when you do this, you have to take into account that you have multiple cores. And on this core, it may have it may be 0, but on the other core, the same bit may be already with 10 segfaults.
You mean that this array is per CPU, right?
This array is global, and this is why for all CPUs, it's updated from all CPUs, but it's checked only on single CPU.
Okay, thank you.
Thank you. The next question.
Hello, my name is Konstantin. Yeah, closer. So, and what about Java applications? If I'm not mistaken, they use segfaults, and this is a normal behavior. They detect that they need to precompile more code before they execute the execution.
This is why I said we're a shared hosting provider, and this is not a big issue. We don't see any valid reason on shared hosting to have an application segfaulting and handling its own segfaults. It's possible. I said this is not a general purpose. It doesn't work for everyone. Unfortunately, this is why we didn't even propose this to the kernel mailing list, because it's plain stupid for general purpose.
Okay, one more question.
So does it help you to mitigate all known kinds of side channel attacks?
No. It helps us to fight every side channel attack that uses segfaults, and that is running similar to Meltdown, because it doesn't protect you from Spectre, because the Spectre attacks speculate within the same process without actually dying. So it doesn't protect you from foreshadow. However, for foreshadow, you could use force entry route with segfaults, which would actually trigger our protection.
Okay, thank you.
Thank you.
Do you intercept the affinity call in the userland or in the kernel?
Oh, in the kernel. We simply patched actually we live patched the shed set affinity directly to replace it with our own function that does this.
Thank you.
One additional question. Do you have any numbers of performance impact of your mitigation?
No, but what I can say is that based on what we have seen on our machines, KPTI is degrading the machines more than our own approach.
It depends on the workload.
Yes, we didn't did static performance tests. We simply rushed it because it was obvious it's a big security risk for us. We rushed it to production where it was tested, but after that we only tested it as, is it working? Does it fail? Does it break anything? If it works, we didn't do performance tests. We didn't have time for this.
It would be interesting to see the numbers.
Yeah, definitely.
Thanks.
Okay, one more question.
Did you use any software to attack?
We used the exploits that were from the public GitHub repos, and a few. There are 2 other exploits from Packet Storm Security, and these are the exploits that we use to test this thing. And the interesting thing is that on our infrastructure for 1 year, we didn't have one exploit attempt except our own tests.
Yes, thank you.
Thank you. Are there any other questions?
Here.
Okay.
Thanks for your talk. What about, are you planning to make a hardware change in your processors to prevent this attack?
There are, but they're not hardware changes, they're microcode updates. And some of these microcode updates cost you more performance also, like in the terms of 5 to 7%. And for these performance degradations, you can actually get the stats from the PostgreSQL guys. They published statistics for this. Maybe there would be changes in the hardware, but as you know, it's not very easy to simply create a new infrastructure for a CPU. It would be a few years, maybe.
We hope.
Yeah.
Okay, probably it's time for the last one. Looks like no. So, what is the best one you received?
I think here.
Okay. Thank you very much, and you'll get.
Thank you.
Thank you very much for your presentation. The next talk is this.